Imagine a future communications network where a message cannot be covertly monitored without leaving immediate physical evidence behind. This is not because the password is more complex, nor because the encryption code is simply harder to crack, but because the fundamental laws of quantum physics actively protect the information. Surprisingly, one of the most promising hardware components for building this revolutionary network begins with something that sounds entirely useless: a microscopic flaw inside a diamond. Physicists deliberately engineer tiny imperfections, known as nitrogen-vacancy centers. Here, a single nitrogen atom replaces a carbon atom, sitting right beside an empty space within the crystal lattice. Around this exact defect, researchers can manipulate individual quantum spins, link them to particles of light, and store fragile quantum data in nearby atomic nuclei. These intricate systems are already being tested as the foundational building blocks for quantum network nodes. While they are not yet forming an impervious global network, they hold the key to solving one of physics' hardest problems: preserving and distributing quantum entanglement across vast distances. To understand exactly why, we must first look deep inside the diamond itself. A diamond seems like the absolute last place anyone would look to find the future of global communication. It is renowned for its extreme hardness, flawless transparency, and an almost perfectly ordered internal crystal structure. Normally, every carbon atom sits in a precise, repeating lattice, locked tightly to its neighbors. Yet, quantum engineers are specifically drawn to the exact locations where that perfect order is broken. One of the most highly valued anomalies is the Nitrogen-Vacancy center, or NV center. It occurs when a nitrogen atom usurps the position of a carbon atom, leaving an adjacent space entirely vacant. That microscopic anomaly alters the electronic framework of the surrounding crystal. Rather than acting like an ordinary gemstone, the defect generates unique quantum states that scientists can actively control using lasers and microwaves. Functionally, it serves as an artificial atom trapped perfectly inside a solid state. This is incredibly valuable because quantum information is notoriously fragile. A standard computer stores data as basic bits, existing rigidly as either a 0 or a 1. A quantum computer operates using qubits, which can exist in complex combinations of states and become deeply entangled with other qubits. These unique traits give quantum technology its immense power, but they also make the data extremely vulnerable to environmental noise. Minuscule shifts in heat, stray magnetic fields, vibrations, or even nearby atoms can collapse a quantum state, a disruptive process known in physics as decoherence. A viable quantum network node must therefore balance two seemingly impossible traits. It must be perfectly isolated to shield quantum data, yet open enough to transmit that data to the outside world. NV centers provide an extraordinarily rare balance. The electron spin anchored to the defect can be initialized, manipulated, and precisely measured. Laser pulses can excite the system, allowing scientists to read its quantum state. Directed microwaves can physically rotate the electron spin to execute controlled commands. Most importantly, this electronic state can easily interact with photons, which are the ultimate vehicles for carrying data through long optical fibers. But the electron is only half the equation. Surrounding this NV center, researchers can often pinpoint individual carbon-13 atoms. While standard carbon lacks a usable nuclear spin, carbon-13 possesses one. Its nucleus acts as an entirely separate quantum vault. These neighboring nuclear spins are incredibly precious because, under the right conditions, they can safeguard data far longer than the active electron can. This creates a brilliant division of labor within the crystal. The electron spin acts as the rapid communication qubit. It engages with photons and continuously attempts to forge entanglement with distant nodes. Meanwhile, the adjacent nuclear spins serve as quiet memory qubits. They silently hold the quantum states while the electron manages the chaotic work of establishing an optical connection. This architecture is vital because quantum networking relies on relentless trial and error. A photon might vanish within a fiber cable. A sensor might fail to detect it. A connection attempt might simply collapse. The node must often try hundreds, sometimes thousands of times. If the delicate memory was wiped every time the communication qubit fired, the entire network would shatter. Therefore, breakthrough experiments with synthesized diamonds have focused heavily on shielding those nuclear memories, while the electron handles the turbulent optical transmission. Recent breakthroughs confirm that carbon-13 memories can withstand vast numbers of communication cycles when properly managed. This elevates the diamond from a single fragile qubit into a microscopic, specialized quantum processor. The material itself can even be custom engineered. Lab-grown diamonds can be synthesized with exact isotopic ratios. Engineers can strip away magnetic interference, place defects with pinpoint precision, and carve microscopic optical tunnels right down to specific NV centers. Engineers no longer have to rely on random stones pulled from the Earth. They can construct the exact atomic ecosystem necessary for a functional device. While this shouldn't be mistaken for a mass-produced microchip, as perfectly replicating these devices at scale remains an immense hurdle, the core theory is proven. The defect works because it anchors a controllable quantum system inside the most durable solid known to science, while the surrounding nuclei cleanly separate communication from memory. This solves the first grand challenge of a quantum network. A node must be able to forge new connections without instantly erasing what it already knows. Classical routers simply duplicate electronic signals. Quantum states, governed by the no-cloning theorem, cannot be perfectly copied on demand. A quantum router needs authentic quantum memory to hold one fragile state while waiting for the next link to open. That is exactly why one missing carbon atom changes everything. To grasp why these microscopic diamond flaws are the key to global networks, picture two high-tech laboratories situated on opposite sides of a sprawling city. Inside each lab sits a supercooled cryogenic chamber holding a custom-engineered diamond. Inside each diamond rests a single NV center. These two defects will never physically touch. Their electrons will never cross the city. Yet, the goal is to entangle these two distant spins. Entanglement is the ultimate currency of quantum communication. When two systems are entangled, they share a profound correlation that defies standard classical physics. While measuring one doesn't allow for faster-than-light messaging, this invisible bond can be harnessed for extraordinary tasks like quantum teleportation and highly secure data distribution. The supreme challenge is forging that bond across miles of physical space. Photons are the perfect couriers because they can traverse optical fiber with minimal environmental interference. In standard protocols, each diamond attempts to bind its electron spin to a single emitted photon. These photons from the two distant labs are then fired toward a central meeting station. There they overlap and are measured. Under flawless conditions, a specific measurement result acts as a definitive confirmation that the two distant matter qubits are now deeply entangled. This breakthrough process is known as heralded entanglement. The term heralded is crucial. The network doesn't blindly assume the link worked. A specific detection event loudly announces that the delicate quantum bridge has been established. This is mandatory because photon loss is a brutal reality. Photons get trapped in the device, fade out in the fiber, or fail to register on the sensor. A functional network must definitively know the difference between a successful link and a failure. NV centers present a unique optical hurdle. The photons they naturally emit glow in the red visible spectrum, around 637 nanometers. However, commercial telecommunications fiber is built for infrared light, where signal loss is drastically lower. Firing native red photons across a city would result in massive signal decay. To bridge this gap, scientists pioneered quantum frequency conversion. They effectively shift the photon's wavelength into the infrared telecom band without shattering the fragile quantum data it carries. This isn't just changing the color of light, it's a surgical translation that maintains the absolute coherence required for quantum interference. In recent metropolitan tests, these altered photons have been successfully beamed through actual underground city fiber grids. This marks a massive leap from pristine lab environments to the chaotic real world. In a lab, lasers rest on vibration-proof tables in climate-controlled rooms. Underneath a city, the environment is hostile. Underground cables expand with heat. Subways cause mechanical tremors. To survive this, Distant diamond nodes require hyper-advanced stabilization systems that instantly correct for environmental drift, alongside atomic-level synchronization, so that photons arriving from miles apart appear completely identical to the sensors. In a landmark 2024 achievement, scientists successfully triggered heralded entanglement between independent solid-state nodes across a live city grid. Separated by miles of deployed fiber, the nodes proved that NV-based networks could survive the real world. Yet, this experiment also highlighted the brutal math of scaling up. Every additional mile destroys more photons. If you attempt to connect a node in New York directly to London, the odds of a single photon surviving the journey are practically zero. The classical internet solves this with standard repeaters, devices that catch a fading signal, copy it, boost it, and send it back out. But because quantum states cannot be copied, quantum networks require an entirely different blueprint. Instead of one impossibly long connection, the distance is chopped into smaller, manageable segments. Neighboring nodes establish local entanglement. Quantum memories securely hold those local links, while the next segment down the line attempts to connect. Once two adjacent links are active, a middle node performs a brilliant maneuver called entanglement swapping. This binds the two outer nodes together, even though they never exchanged a single particle. By repeating this swap down the chain, the network can stretch entanglement across continents. This is the holy grail, the quantum repeater. And this is exactly where the diamond's nuclear spins become mandatory. The electron works frantically to build the next bridge, while the stable carbon-13 nucleus safely holds the ground already gained. Without that local memory, a hard-won connection would vanish before the next link could even fire. Linking two machines proves a concept, but an actual internet requires complex routing, stable memory, error management, and the ability to bridge devices that share no direct physical line. To prove this was possible, researchers scaled up to small networks where different processors handled distinct jobs. In a groundbreaking trial involving 3 distinct nodes, traditionally labeled Alice, Bob, and Charlie, scientists proved that independently controlled quantum processors could distribute entanglement in a true network formation. While 3 nodes seem microscopic compared to the modern web, it represents a monumental paradigm shift. The middle processor, Bob, can lock in a link with Alice, store that data, forge a second link with Charlie, and then merge the two. This is the exact mechanism a future global repeater will use. The magic lies in entanglement swapping. If Alice is entangled with one side of Bob, and Charlie is entangled with the other, Alice and Charlie have no direct relationship. But by executing a highly specific joint measurement, Bob can instantly bind Alice and Charlie together. The entanglement isn't physically handed off. The relationship is forged by manipulating the larger system. By 2022, engineers utilized this exact architecture to execute quantum teleportation between non-adjacent nodes. While teleportation sounds purely like science fiction, it doesn't mean matter vanishes and reappears. Instead, a quantum state is transferred by leveraging shared entanglement in classical communication. The original state is dissolved, and its exact replica is reconstructed miles away. This process still obeys the speed of light, but it means quantum data doesn't have to physically travel the entire perilous journey as a single fragile particle. A chain of entanglement acts as a secure highway. However, as networks grow, so does the margin for error. A slight laser miscalibration, stray magnetic noise, or a failed optical pulse can corrupt the system. Long-distance networks heavily magnify these tiny flaws. While standard computers use robust codes to detect and correct data degradation, quantum correction is notoriously difficult because directly observing the data destroys it. To bypass this, researchers spread the data across multiple physical qubits, allowing them to detect environmental degradation indirectly. Advanced NV center platforms have successfully tested these techniques, combining electron spins, memory nuclei, and photons to suppress specific errors without looking directly at the data. Simultaneously, engineers have dramatically improved the hardware's biggest bottleneck, photon collection. A brilliant quantum memory is useless if its photons can't escape the crystal. By carving microscopic optical cavities directly into the diamond, Modern experiments have drastically boosted the number of usable photons that enter the fiber network. In a system built on probability, capturing even a fraction more photons exponentially speeds up the network's connection rate. By 2026, experiments advance from teleporting static states to teleporting actual computational commands. Researchers successfully fired a remote, controlled NOT logic gate between separated quantum registers. This proves that a future network won't just transmit secure keys. It will allow physically separated machines to combine their processing power into a massive, distributed supercomputer. The concept of an invulnerable quantum internet captures the imagination, but it requires precise scientific context. Quantum communication introduces security architectures that are fundamentally alien to standard digital networks, though physics alone does not magically grant absolute invincibility to every piece of hardware. Modern digital security relies heavily on complex mathematics. When you access a secure banking portal, the protection stems from mathematical puzzles that are virtually impossible for standard computers to solve in a realistic time frame. The security assumes the computational barrier is too high. However, future fault-tolerant quantum computers could, in theory, shatter these mathematical walls in seconds. A quantum internet pivots entirely away from math-based defense. Instead, it uses the raw laws of physics as a shield. In protocols like quantum key distribution (QKD), remote users generate shared encryption keys using delicate quantum states. The security is anchored in the absolute rules of quantum measurement. An unauthorized third party cannot observe an unknown quantum state without permanently altering its statistics. The network instantly detects the interference. Furthermore, the no-cloning theorem ensures that quantum data cannot be perfectly duplicated or siphoned off unnoticed. These physical laws provide guarantees that standard encryption can never match. However, this does not mean data breaches are scientifically impossible. Real-world networks rely on physical hardware. Lasers can be miscalibrated. Control electronics can be bypassed. A user's local machine might be running malicious code, or an unauthorized user might extract access codes before the advanced quantum protocol even initiates. Researchers continuously point out that practical systems can have physical blind spots if the actual machinery deviates from the theoretical physics models. Therefore, the most accurate way to view this technology is not as a magic shield that ends all cyber threats. It is a system where specific forms of network interception become immediately physically detectable. A future quantum web will likely run parallel to our current infrastructure. Standard networks will still handle routine routing, user interfaces, and coordination. The ultimate security of the system will depend on the strength of the entire chain, not just the glowing diamond at the center. The true revolution lies in the new resource it provides: distributed entanglement. This invisible bond will allow distant systems to synchronize measurements, link remote processors, and execute operations we are only just beginning to theorize. The profound challenge remains pushing this resource across oceans. A fully realized global network will demand repeaters that can seamlessly catch, store, correct, and forward these delicate states. Diamond NV centers remain a premier candidate because they have successfully demonstrated almost every single required step within one microscopic package. Of course, Diamond is not the only contender. Global laboratories are fiercely testing silicon vacancy centers, trapped ions, neutral atoms, and rare earth elements. Each architecture brings distinct advantages. A mature network will likely be a hybrid, perhaps utilizing diamonds for stable memory storage, while different materials handle the rapid long-distance transmission. This intense global race emphasizes just how monumental the engineering challenge truly is. Scientists must perfectly safeguard quantum data while relentlessly firing optical lasers. They must stabilize thousands of miles of shifting underground fiber. They must seamlessly convert light spectrums without shattering the quantum states hidden within. The vision of an entirely invulnerable global network remains the ultimate horizon, not a finalized product. The hardware does not yet cross oceans, and massive repeaters remain in the testing phase. Yet, the required pieces of physics have moved from chalkboards into reality. Metropolitan fiber is carrying entangled light. Remote logic gates are firing across cities. What was once dismissed as a minor flaw inside a gemstone has become the exact blueprint for how the next era of human communication might be built.
Look closely one final time at the exact microscopic space where the diamond lattice breaks. One nitrogen atom sits quietly beside an empty void. When you zoom into that precise atomic scale, the future of global communication doesn't resemble a massive server farm, a steel satellite dish, or a glowing fiber optic cable. It looks exactly like an imperfection. By harnessing that specific flaw, physicists have learned to control electron spins, vault quantum data inside neighboring nuclei, bind those states to light, and beam entanglement across cities. The global quantum internet is not fully built. Its repeaters are still being refined, its memories are being optimized, and its advanced security will always require flawless real-world engineering. But the trajectory of science is unmistakable. The classical internet conquered the world by learning how to perfectly copy and blast data between millions of machines. The quantum internet is attempting something far more profound, distributing the deeply fragile, beautifully complex architecture of entanglement itself. And if this network eventually spans our continents and oceans, its foundation will be built on a lesson that nature constantly reminds us of. Absolute perfection is rarely where the most powerful discoveries are made. Sometimes, the most valuable piece of a crystal is the exact atom that is missing,